A widening emergency in Southern California forced tens of thousands of residents from their homes after authorities discovered a dangerous crack in a massive industrial chemical tank containing methyl methacrylate, a highly flammable and toxic compound widely used in plastics manufacturing. Streets emptied across parts of Garden Grove as firefighters and hazardous materials teams worked around the clock to cool an overheating storage vessel at a facility operated by GKN Aerospace. The situation raised urgent questions far beyond a single industrial site. How close had the region come to a large-scale chemical disaster? How dangerous would a release of methyl methacrylate become if vapors spread into densely populated neighborhoods? And how vulnerable are modern urban centers when industrial chemical infrastructure begins to fail only a few miles from homes, schools, highways, and major tourist destinations? The emergency centered on a storage tank holding approximately 6,000 to 7,000 gallons of methyl methacrylate, equivalent to roughly 22,700 to 26,500 liters, at an aerospace manufacturing complex in Garden Grove. Officials warned that the tank had entered a dangerous thermal condition after temperatures inside the vessel continued climbing over several days. Fire crews repeatedly sprayed water over the structure in an attempt to reduce the heat load and prevent the contents from destabilizing further. Authorities feared two possible outcomes: a catastrophic rupture that could scatter burning chemicals and debris across the surrounding area, or a large toxic release capable of spreading airborne contamination through nearby communities. The discovery of a crack in the tank introduced both relief and new uncertainty. Emergency officials indicated that the fissure may have partially relieved internal pressure that had been building as the chemical heated and expanded. That development reduced fears of an immediate boiling liquid expanding vapor explosion, commonly known as a BLEV, but it did not eliminate the threat. The damaged tank still contained thousands of gallons of hazardous material, and authorities remained concerned that additional structural failure or leakage could occur at any moment. The scale of the response reflected the seriousness of the danger. Roughly 50,000 residents fell under evacuation orders at the height of the emergency. Entire neighborhoods were cleared while emergency shelters opened across Orange County. Major roads near the industrial zone were shut down as specialized crews monitored temperatures, atmospheric conditions, and vapor concentrations around the clock. Drones equipped with thermal imaging systems repeatedly surveyed the tank from above because responders considered direct close-range inspection too risky during peak heating conditions. At the center of the crisis stood methyl methacrylate, commonly abbreviated as MMA, an industrial chemical that occupies a critical place in modern manufacturing. The compound is used extensively in the production of acrylic plastics, transparent panels, coatings, adhesives, resins, flooring compounds, medical materials, automotive components, aircraft parts, and countless industrial products. In stable conditions, MMA is a colorless liquid with a strong, sharp odor. Under unstable thermal conditions, however, the chemical becomes significantly more dangerous. Methyl methacrylate is highly flammable. Its vapors can ignite rapidly when exposed to sparks, static discharge, open flame, or sufficiently high heat. More concerning for emergency responders is the compound's tendency to generate heat during polymerization reactions. Under certain conditions, especially inside confined storage systems, MMA can begin reacting in ways that accelerate internal temperature increases. Rising temperatures increase vapor formation. Rising vapor formation increases pressure. Increasing pressure then raises the risk of structural failure in storage tanks or pipelines. That chain reaction became the defining fear during the California emergency. Authorities monitoring the Garden Grove tank reported temperatures climbing toward approximately 100 degrees Fahrenheit, or nearly 38 degrees Celsius, during the peak of the incident. Fire officials warned that instrumentation limitations prevented them from fully confirming how much hotter certain internal sections of the tank may actually have become. Emergency crews focused on continuous cooling because thermal runaway conditions inside chemical storage systems can escalate extremely rapidly once stabilization measures fail. The toxicity concerns surrounding MMA added another layer of urgency. Although methyl methacrylate is widely used in industry under controlled conditions, airborne exposure at elevated concentrations can produce serious health effects. The compound is known to irritate the eyes, nose, throat, and respiratory system. Individuals exposed to concentrated vapors may experience coughing, burning sensations, chest tightness, dizziness, nausea, headaches, confusion, and shortness of breath. Prolonged or intense exposure can affect the central nervous system and may impair breathing in sensitive individuals. The danger becomes particularly severe in large airborne releases because MMA vapor is heavier than air under many conditions. That means the chemical can accumulate in low-lying areas, enclosed structures, drainage systems, or confined outdoor spaces. In an urban environment, vapor clouds can travel unpredictably depending on wind speed, humidity, atmospheric stability, and temperature inversions. A release occurring during calm nighttime conditions could potentially allow concentrated vapor pockets to persist near the surface longer than expected. Emergency planners feared exactly that scenario. Garden Grove and surrounding sections of Orange County contain dense residential zones, commercial districts, schools, transportation corridors, and entertainment destinations packed into relatively small geographic areas. A major airborne release in such an environment would not behave like a remote industrial spill occurring far from population centers. Vapor movement through suburban streets, parking structures, drainage channels, warehouses, and apartment complexes could create highly uneven exposure patterns. Some areas might experience limited contamination, while others encounter dangerous concentrations depending on wind shifts and terrain interactions. Officials repeatedly emphasized that air monitoring around the evacuation perimeter did not initially detect significant hazardous concentrations. Still, the absence of a confirmed major release did not eliminate the threat because the tank remained unstable for days. The possibility of ignition represented another severe concern. MMA vapor is not merely toxic, it is combustible. If a substantial vapor cloud formed and encountered an ignition source, the result could involve flash fires, secondary explosions, or rapidly spreading industrial fires, affecting nearby structures and storage systems. Authorities worried that an uncontrolled event at one tank could spread heat and fire to adjacent industrial materials inside the aerospace facility. Containment operations therefore extended beyond cooling the damaged vessel itself. Crews established barriers and protective systems designed to prevent spilled chemicals from reaching storm drains, waterways, and ultimately the Pacific Ocean. Environmental protection measures became increasingly important as responders prepared for the possibility that the tank could partially rupture or leak while cooling operations continued. The incident also exposed the complexity of managing unstable chemical reactions once critical industrial safety systems begin malfunctioning. Reports indicated that damaged valves limited responders' ability to safely neutralize or transfer the material inside the tank. Under normal conditions, industrial chemical storage relies heavily on layered safety mechanisms, including cooling systems, pressure relief devices, emergency venting equipment, chemical stabilizers, instrumentation monitoring, and controlled transfer procedures. When multiple systems fail simultaneously during an overheating event, responders can find themselves with very limited options. That reality shaped emergency strategy in California. Firefighters could not simply drain the tank immediately because manipulating unstable chemical systems under high pressure risks triggering the very failure crews are attempting to prevent. Direct intervention near the vessel also exposed responders to potential blast hazards and toxic vapor release. Instead, crews relied heavily on external cooling and remote monitoring while waiting for internal conditions to stabilize enough for closer assessment. The crack discovered in the tank eventually appeared to reduce internal pressure sufficiently to lower the risk of catastrophic explosion. Temperatures later declined into the lower 90s Fahrenheit range, equivalent to approximately 33 to 34 degrees Celsius, allowing authorities to cautiously ease some evacuation restrictions. Even so, officials stressed that the situation remained dangerous. A cracked chemical tank holding thousands of gallons of volatile industrial material does not instantly become safe simply because explosion risk decreases. Leakage concerns, residual vapor hazards, structural instability, and environmental contamination risks can persist long after immediate thermal threats subside. The incident also demonstrated how chemical emergencies can evolve unpredictably over time. At first, authorities concentrated almost entirely on preventing a violent explosion. Once the crack emerged, attention shifted toward leak management, atmospheric monitoring, and long-term stabilization. Emergency zones had to be adjusted continually as new information emerged regarding tank integrity and internal temperatures. Scientific modeling of potential release scenarios likely played a major role behind the scenes throughout the response effort. Hazardous materials teams routinely use atmospheric dispersion models to estimate how toxic plumes might travel under different weather conditions. Variables including wind direction, temperature, solar heating, humidity, terrain roughness, and atmospheric stability all influence how chemicals disperse after release. In coastal Southern California, weather patterns can shift rapidly between daytime heating cycles and nighttime marine air influences, complicating forecasting efforts. A worst-case methyl methacrylate release scenario in a heavily populated urban region would depend on several interacting factors. A slow leak with controlled ventilation would behave very differently from a sudden tank rupture accompanied by fire. In one situation, responders might focus primarily on respiratory protection and shelter-in-place guidance. In another, they might confront simultaneous toxic exposure risks and rapidly spreading industrial fires. If large quantities of methyl methacrylate entered the air quickly, immediate symptoms among nearby populations would likely include intense odor detection, eye irritation, throat burning, coughing, headaches, and respiratory distress. Individuals with asthma, chronic lung disease, cardiovascular conditions, or chemical sensitivities would face elevated risk. High vapor concentrations in enclosed or poorly ventilated areas could potentially displace breathable air and increase inhalation exposure. Another concern involves secondary contamination. Methyl methacrylate vapors can settle onto surfaces or infiltrate structures through ventilation systems and openings. Following a significant release, buildings near the affected zone might require environmental testing and decontamination before safe reoccupation. Industrial spills involving volatile organic compounds often create lingering odor and air quality concerns even after the primary release has ended. Environmental consequences would also depend heavily on release scale and containment success. Methyl methacrylate can evaporate relatively quickly in open air, but spills into drainage systems or waterways may threaten aquatic ecosystems and require specialized cleanup operations. Preventing runoff into creeks, storm drains, and coastal waters therefore became a priority during the Garden Grove response. The location of the incident amplified public concern because of its proximity to major population centers and internationally known destinations. Garden Grove sits near Disneyland Resort and other heavily visited parts of Orange County. Although the evacuation zone did not include the resort area, the incident highlighted how industrial infrastructure and dense urban development increasingly overlap across major metropolitan regions. Large chemical storage systems often operate quietly for decades with little public attention. Yet many metropolitan residents live only a few miles from facilities containing volatile industrial compounds used in aerospace manufacturing, plastics production, energy processing, semiconductor fabrication, water treatment, and transportation systems. Emergencies involving those materials can escalate rapidly because surrounding urban growth eventually places more people near legacy industrial corridors originally built farther from residential zones. The California incident also underscored the importance of chemical-specific emergency planning. Not all industrial chemicals behave the same way during overheating events. Some primarily threaten groundwater contamination. Others generate corrosive gases. Others become explosive under confinement. Methyl methacrylate presents a particularly difficult combination because it is simultaneously flammable, volatile, chemically reactive under certain conditions, and harmful when inhaled at elevated concentrations. Thermal instability remains one of the most feared conditions in industrial chemical management because once exothermic reactions accelerate beyond control, standard cooling systems may struggle to remove heat fast enough to prevent runaway escalation. That concern has shaped chemical safety engineering for decades across multiple industries. Emergency officials in California repeatedly described the operation as delicate and highly controlled because aggressive intervention itself can sometimes worsen unstable chemical conditions. Rapid pressure changes, vibration, static discharge, or sudden chemical movement inside partially reactive systems may trigger unexpected reactions. Responders therefore balanced the need for active cooling against the risks associated with direct tank manipulation. By the beginning of the week, following the initial emergency, officials announced that the threat of catastrophic explosion had largely subsided after confirmation that the crack relieved internal pressure. Still, monitoring operations continued while crews worked toward long-term stabilization and safe handling of the remaining chemical inventory. The broader implications of the incident will likely continue attracting scrutiny because the emergency unfolded in one of the most densely populated industrial corridors in the United States. Questions surrounding equipment maintenance, monitoring systems, valve failures, emergency preparedness, evacuation logistics, and industrial oversight have already emerged as authorities assess the sequence of events that push the tank toward instability. For nearby residents, the incident became a stark reminder that modern industrial systems depend on continuous control of heat, pressure, chemistry, and containment. A single compromised storage vessel holding a volatile industrial compound triggered evacuation orders affecting tens of thousands of people and mobilized a massive emergency response operation across Southern California. The visible crack in the tank eventually became the feature that may have prevented a larger catastrophe. Yet the same fissure also symbolized how narrow the margin can become once industrial containment systems start failing under thermal stress. Inside that damaged vessel remained thousands of gallons of a chemical capable of producing toxic vapors, rapid combustion, and escalating pressure under unstable conditions. For several tense days, one overheated tank transformed into a regional hazard zone, monitored minute by minute by firefighters, hazardous materials specialists, environmental agencies, and emergency planners trying to prevent a dangerous industrial chain reaction from unfolding in the middle of suburban Orange County.